Good morning. It's my pleasure to be here. So I was planning to do 3 talks, one on resonant energy transfer from 300 Kelvin to 300 microkelvin. The second one on the interactions of atoms with strong fields, which in our case would be microwave fields. And finally on a talk about 2 electron atoms. So today I'm going to start with resonant energy transfer from 300 Kelvin to 300 microkelvin. This is a list of the people with whom I've worked on this subject, starting with Kambi Safina a long time ago, and Pierre Piet. You recognize probably some of these names. Bob Stone and Ray, Thompson, Anderson, Dale, Robinson, Noel, Martin, Lee, and Park. So today people are interested in dipole-dipole energy transfer in cold Rydberg systems, partially because of the potential for quantum gates, but also because you can construct model systems of interacting atoms that you can imagine actually controlling and manipulating in ways that you couldn't do with many other systems. Historically, however, and why we actually started to do this was the notion that in many practical contexts, it turns out that in collisions, resonant energy transfer from species A to B is important. And while today the helium-neon laser is not so ubiquitous as it was 15 years ago, the first laser ever made was the helium-neon laser, and it actually worked because of resonant collisional energy transfer. I mean, in the discharge, helium population piles up in these 2 metastable 2s states. And in fact, helium atoms in either of these 2 states can hit a neon ground state atom and exchange the energy resonantly, as shown by these 2 green arrows. And in fact, then these levels are in fact the upper laser levels of the neon laser transitions. So this is the 3.39 micron transition, this is the red 6328 line, and this is the 1.15 micron infrared line of neon. So, okay, presumably this resonant transfer is important. In some ways, the experimental evidence that it's important is that there is no helium arc laser, no helium krypton laser. There's only the helium neon laser. Okay. But in some ways, what you would like to do is to actually study sort of resonant collision processes like this in a more systematic fashion. And the Rydberg states actually provide a way that you can imagine doing this. And one of the first examples of this is, I think, a very pretty experiment done at Rice. And of course, one of those doing at Mary Dunning is not so visible here now. So the idea of this experiment is fairly straightforward. There's a xenon beam, which is excited by a pulse laser to the 27S state by a laser beam. And it's in the presence of an ammonia gas. And so the objective is then to look at the population transfer from 27S to F to other states. And what they in fact see when they do the experiment is the following. So the pulse laser excites the atoms, collisions happen for up to 10 microseconds, and then a field is applied, an electric field, to field ionize the atoms. So if there's no ammonia in this field ionization signal, which is a plot of the signal determined as a function of time here, basically, you see a spike right here from the 27S state that ionizes at that field. When you put, and basically nothing else. There's a little bit of other stuff, but I won't get into that. It's quite interesting finally, but when you put ammonia in, you can clearly see that there's stuff earlier, which is in higher line states, but it's not everywhere, it's in specific peaks. That is to say, it's in specific end states up here which ionize earlier in the pulse. And if I pick this particular peak, for example, this corresponds to the energy change from n equal 27 up to about n equal 55, where it's resonant with the ammonia j equals 6 to j equal 5 transition. In other words, what we're seeing here is the resonant energy transfer from the ammonia rotational energy into the electronic energy of the Rydberg state. And this, if you actually analyze how much signal you see in terms of how much ammonia you put in, you find that the cross sections for this are between 10,000 and 100,000 angstroms, which is roughly the geometric size of these 27 are xenon atoms. Okay, so I guess I should remind you, if you look at any textbook to see what a gas kinetic cross-section is, it's 100 square angstroms. Okay, so these are rather large cross-sections. Okay. So in some ways, this is like doing absorption spectroscopy. Now, you could also imagine trying the following Gedanken experiment of having two atoms, or two species, could be an atom or molecule, with energy levels like this. A is fixed, and B changes energy level as a function of some parameter. And as I change that parameter, I would imagine that, or I would hope to see, that you could in fact sweep through this resonance and see the cross-section go through a peak at the resonance. Okay. So we decided we were going to do this. And we were, in fact, planning to bring the sodium 16s to 16p transition into resonance with the rotational transition in HBr. And so you can, in fact, relatively easily calculate the field that it should take to do this, and it should be about 500 volts per centimeter, where this transition in sodium matches the HBr rotational transition. This is essentially the same idea as the Rice experiment. So we did essentially the same experiment, and we observed the transition here. It wasn't here. And of course, we thought, well, okay, we're experimental plumbers. We don't expect that we're not necessarily going to calculate all these things right. So we thought, oh, this is great. We're in business. So I then suggested to colleagues, well, let's take the HBr out. And, well, it's still there. Okay. So it's clear this actually has nothing to do with the HBr. Somehow it's just sodium. I mean, it's just the sodium atoms. And what actually is happening is this, that when you excite the 16s state, and in fact apply the electric field, these two P levels go up, and at about 600 volts per centimeter, the 16s state is exactly halfway between these two, and one can go up and one can go down. So it's the same process, same kind of process that we were talking about, thinking we were going to do with HBr, but we didn't need the HBr. Okay, so after realizing that this happened, we then said, okay, this looks like it's a collision, but it's beam-beam scattering. And for those of you who have ever thought about doing something like this, the idea of doing beam-beam scattering is always terrible because the rates are low. So let's estimate the rate at which we should see this process. We know the rate, actually, let's estimate the cross-section. A collision rate, well, that's funny, that was a gamma on my computer, is a product of the number density times, oh, that was a sigma. Okay. I guess we're going to have to get used to this, since we're going to have a few transcription changes. Okay, so the collision rate is the number density times the cross-section times the velocity. We know the rate, it's occurring in a microsecond, so it's 10 to the 6th inverse seconds. The number density in the beam is 10 to the 8th per cubic centimeter. The velocity is 10 to the 5th per cubic centimeter. And so you get a cross-section of 10 to the minus 7 square centimeters, which is 1 billion square angstroms, which of course sounds completely ridiculous. But as I will try to convince you, this is actually right. Okay, so we in fact then decided we would measure these resonant dipole-dipole collisions of sodium atoms. And so here's the example moving up on n state. So you in fact populate the atoms with a pulse laser in this state, let them collide for times that anywhere from half a microsecond to several microseconds. And then we apply a field pulse and we look for the population in this upper P state, okay? Because it's easier to field ionize than the S state. So, as I said, we have a beam, it's thermal, so the fast atoms are always hitting the slow atoms. And by sweeping the field, you can in fact see these resonances at which point the S state is halfway between the two P states. Now, there are actually, you can see there are 4 resonances that correspond to the M values of the P state. The S, of course, has no M value. And so here they are. So you can easily see them. And so I already told you that you can estimate the cross-section as being 1 billion square angstroms. And if you then use the Stark effect to work backward from these widths, you can also figure out the frequency widths. of these resonances. So these resonances correspond to a frequency width of about 1 gigahertz. Okay? So what that means then is that these atoms are colliding for a nanosecond, which may or may not mean anything until you compare it to a gas kinetic cross-section. So if you have thermal atoms and they have gas kinetic cross-sections of 100 square angstroms, the collision time is a picosecond. So at room temperature, these atoms the collision lasts 1,000 times longer than it does for ground state atoms. Okay. Now, oops. All right, so I've claimed that this cross-section, which sounds absurd, is actually right. And so we can actually calculate the cross-section in the following way. That sort of comes from RF spectroscopy. So I'm interested in two atoms, one of which we'll imagine is stationary here, and the other one goes by with a relative velocity v with an impact parameter b. Okay? And so this is, in fact, the dipole-dipole interaction. We're not going to worry about the orientational dependence for the moment. And so I'm going to imagine that this atom that's going by here is producing an RF field at the second atom. So let's say this one is 17S. So it, in fact, has a whole bunch of allowed electric dipole transitions. And so in any one of these, it, in fact, can be thought of as producing an RF field at the point of position of this atom, which is a field that corresponds to this dipole, any of these dipoles oscillating at the correct frequency. Okay. So the one that we're actually interested in is the dipole between 17S and 16P, which oscillates at this frequency. Okay, so it produces this oscillating field at the position of that atom. Okay, so the field from this atom can drive this one from 17S to 17P, just like in a radio frequency resonance experiment, if the magnitude of mu2, that is the 17S to 17P dipole moment, times the field from this one, times the exposure time is equal to 1. Which is, this you recognize as something that looks like a Rabi frequency, so it's just the Rabi frequency times the exposure time is equal to 1. Okay, so this is mu2, and the field E1 we will approximate as just being the dipole moment divided by the cube of the impact parameter. Okay, so it's only, when it's far away, it doesn't do anything. When the field is strong is when this atom is right here. And then we'll use for the time just this distance v divided by the velocity. Okay. So if you set that equal to 1, you find this expression for v squared, and that's basically just the cross-section. So the cross-section is the product of the two dipole matrix elements. These are transition moments. They're not permanent dipoles, divided by the velocity, the relative velocity of the atoms. And so this is in atomic units, and if you figure this out for n equal 20, you find that it's 10 to the minus 7 square centimeters. You can also, of course, calculate the resonance width, or the inverse of the collision time from this, and you find that it scales as a 3/2 power of the velocity divided by m squared, or and so, and at n equal 20, this gives you a 1 gigahertz width. So if you actually measure these, you in fact do find those expected end dependencies. That is, the cross-section goes up as the 4th power of the principal quantum number, and the collision time, that is the inverse of the width, rises as the square of the principal quantum number. The bottom here is n to the 4th, and you can see this goes up with a slope of 1, and this is a slope of 1/2. Okay. So that picture, that simple-minded picture, is actually seems to describe this pretty well. Now, for future use, there's a slightly different way that you can think about this, okay, which is based on what I will call a molecular picture. Well, it's a diatomic molecule picture. And so we're going to make two diatomic states. One, the initial state is WSS, which is two atoms in the S state. So they have and this SS state has the energy, which is the sum of the two S energies. And then the PP state has an energy which is the sum of the NP and N plus 1 p state, or N minus 1 p state, sorry. And the wave functions are actually just direct products of the atomic wave function. So when the atoms are infinitely far apart, the S energies don't change, so they look like this, and the PP energies go up like this and cross them. Okay, so they actually, they of course cross. But at any finite spacing between the atoms, there's an avoided crossing between these two molecular levels due to the dipole-dipole interaction. And that crossing looks like this. Now, so if I in fact focus for a second on the resonance, and it's at this electric field, irrespective of the spacing that I choose between the atoms, the eigenstates actually, oh wow. Okay, so I guess we're also, this was a psi. So we think, well, I guess, so why you could think psi. So the wave function that we have, the two eigenstates are psi minus is SS psi SS, sorry, minus psi PP prime, and we also have, sorry, I went backwards. Oh. Well, okay, things are, yeah, it appears that this is multiply screwed up. Okay. This is psi minus is SS minus P prime, and psi plus is SS plus. I guess I should just get used to this. This is the way it's going to be. Okay, so it doesn't matter what the spacing is. Those are always the at resonance, those are the eigenstates. Of course, these are also the eigenstates, but they're not. These are only good at infinite room to spacing. Okay, so initially the atoms are far apart in the SS state. And the wave function initially is this, which is psi plus psi minus, and we start out here. And then as the atoms come together, of course, the energies of these two states separate and then come back together. I mean, this is the point of closest approach right here. And then on the other side, we recombine these two wave functions, which we split here. And in fact, if the area between these two curves, which is just a phase, is pi, then the final state turns out to be psi plus minus psi minus, which is just the PP state. If you work this out, this gives you exactly the same cross-sections that we had earlier. Oh, that's interesting. So these were, as you can, I'm sure, now imagine, I expected these to be mu's, but 2 slides ago they were, okay. Anyway, all right. But you get the same cross-section. This turns out to be something that we can use. This is a very useful way of thinking about it. I'll come back to that again later. But even for any collision process, it's always true that if I have two atoms that are colliding at some fixed velocity, I can in fact compute the dipole-dipole cross-section as being proportional to the avoided crossing between these two levels at any fixed radius. Okay, so if I now go back to the sort of unique features of these cross sections. I mean, while the cross sections themselves are big, it's not that actually that makes them so interesting. The fact that the atoms are colliding for a long time actually turns out to be really interesting because it lets you do something to these atoms while they're colliding. And so you, in fact, have 3 orders of magnitude more time than you have if you have a couple of runs to the atoms. And you have these enormous handles on the atom, namely their enormous electric dipole matrix elements. So Steve Harris and his students actually were observing what they called laser-induced inelastic collisions. Well, okay. They're sometimes also called radiative collisions, which are the absorption of photons, typically from a very intense laser, while 2 atoms are colliding with each other. And so they, in fact, put strontium atoms in the 5p state in a mixture of strontium and calcium vapors, and they shine in light at this wavelength. They can, in fact, have the strontium atom fall back down here, and the calcium atoms go from the ground state up to this 4p state. So it's while the strontium and calcium atoms are colliding, just while they're together, that molecular transient molecule absorbs this photon, and you can in fact wind up, when they separate, having the excitation purely in the calcium. Okay. So this takes a laser power of 1 megawatt per square centimeter to see anything. Okay. This is not to study it, this is just to see it at all. Okay. So it turns out if you do the same thing using these sodium S2P things I've been talking about, you can see not just the absorption of one, you can see multiple photons. For example, if you consider the 18S state, for example, the resonance that we talked about earlier, the resonance is about 400 volts per centimeter. But if you lower the field, you can in fact see collisions in which there is stimulated emission of 1, 2, 3 microwave photons, that has to happen while these atoms are colliding with each other. But now instead of having a picosecond, we have a nanosecond to do this. So, these experiments are typically done by passing atoms through a microwave cavity where there's a microwave field present and exciting them with the laser. So with no microwave power, you see the same 4 resonances that I showed you earlier. They're a little closer together now because it's a higher N state. With 20 milliwatts of power, you can still see this, but you can see the analogous 4 states in which there's been stimulated emission of 1 photon during the collision. At 300 milliwatts, you can see the 4 resonances corresponding to the stimulated emission of 2 photons. And and you can sort of see that as you go higher, you can now see 3 photons, and here's 3 photons again. And the other thing that's kind of interesting to observe here is that at this point, the 1 photon transitions have gone, right? So, I will come back to this in some more detail in the next lecture, but you can actually work this all out, including the fact that some of them disappear, etc. in terms of the dipole-dipole collisions between microwave-dressed atoms. And I will talk more about this the next time, but that, in fact, leads you to the notion that the cross-sections for collisions in which there's a stimulated emission of m photons is the cross-section with no microwaves multiplied by the special function, where this is the sum of the star shifts of those 2 p states, and that's the microwave field. This is, in fact, a graph of the expected and observed cross-sections, and you can see that it pretty well matches. Okay, so, all right, so that's what just using what nature gives you can see that. But if we come back to the velocity dependence, the width of those resonances should in fact go down as the 1 over the 3/2 power of the velocity. And so, in fact, the velocity dependences of these has been investigated in several, in 2 different ways using the same system, which is now potassium. It turns out if you put potassium atoms into the 29S and 27D states at fields of around 6 volts per centimeter, you in fact can see collisional resonances corresponds to the S state going up to 29P and the D state going down to 28P. Okay. So I will show you a way that how we did this originally, but I will point out that it's been done by, and I'll explain a much more clever way that's been done by my colleague Bob Jones and his student Mary Cudrow. Okay, so the original caveman experimental approach is shown here. It's a beam of potassium, and if you have a velocity selection wheel, you let through a pulse of atoms, and then about 100 microseconds later, you send a pulse laser in here, you've selected 1 velocity group of the atoms. Okay? And so you can in fact get down to a temperature of about 1 Kelvin this way. Okay. And so this apparatus actually is in a vacuum chamber, which has a liquid nitrogen trapped in it. So, of course, I will now recommend the right way to do this, which is Bob Jones' method. So his beam goes along here, and he excites it with a 10 nanosecond laser pulse. Okay. So I now have made a slice of Rydberg atoms that's as wide as the laser pulse. And so if I just wait a few microseconds, the beam is going this way, so the fastest atoms are now moved down to here. The slow atoms have only moved here. But the point is, in any area here, you only have one velocity group of atoms. Okay, so you immediately can velocity select the whole, you can see all the atoms with a small velocity distribution. Okay, so but if I go back to this method, it turns out if you don't put liquid nitrogen in this trap, you have a cell of atoms. Contrary to the published vapor pressures of potassium, if you don't do anything at room temperature, you have it all over the place. So we, in fact, can see this resonance as 240 megahertz wide. So this is making this S and D pair and looking for the P state up above. If you put nitrogen in the trap, now you have all the atoms going this way. You no longer have them going in every possible direction. It's 50 megahertz wide. And if you now velocity select it to 1 Kelvin, you find something that's 6 megahertz wide. So curiously, we did that. We were very happy when we saw this. And later realized that actually it has this width because of the Earth's field. If you cancel the Earth's field, it's only 1.25 megahertz wide. Okay. 1.4. So now these are actually collisions that are lasting a microsecond. So this, so the collisions now are lasting about as long as the time that you let them collide. And this leads immediately to the following notion. What happens if I actually sort of start squeezing the time that they're allowed to collide? So when we let the atoms collide for 3 microseconds, we get this 1.4 megahertz wide collision that I advertised earlier. Okay. And if I shorten it to 2 microseconds, it gets a little wider, it gets a little sharper. But once I start shortening that time to below a microsecond, it's clear that this becomes much broader. It's, of course, just transform broadening. I mean, but what this actually means is, when I get up into this regime, I know when the collision started and I know when it stopped. Okay, so I can now perturb it at well-defined points in the collision, at least if this notion is correct. And so, this is basically saying what oops, sorry. So once we get into this regime, so initially, in fact, what happens with the detection pulses way up here, you can get all kinds of these collisions with varying times of collision. When you shorten it down, the only ones that you see are ones that start here and finish here. I mean, you don't. That's all you can see. Ones that are okay. It's true that there can be ones that occur in much shorter times, but there are very few of them, and of course they are very broad resonances. Okay. So, all right. So let's use this. So we decided that we would continue the notion of what happens if you have these atoms collide in the presence of a radiation field. So, in fact, if you put in an RF field that's synchronized with this allowed collision time, you get wildly different results if you have sine and cosine. So if you have a sine field so that the field looks like this during the collision, what it does is bring the initial state into resonance with the final state, which you can barely see here, twice, once here and then once here. So what actually happens then is that as it passes through this point, the wave function splits, and you basically make an interferometer. And if you then analyze what happens as you change the tuning field, which is moving this level up and down, you see these oscillations, which in fact correspond to what are sometimes called Zuckerberg oscillations. They're obviously also related to Ramsey frames. This is what you see with no RF field. You see a resonance here. And in fact, with the sine field, you see these Zuckerberg oscillations. With the cosine field, it's obvious that no matter where I tune the other level, it only comes into resonance once. And so what you see is this really big blob. And it turns out you can, in fact, work out how you connect this back to that Russell function description. I will come back to that tomorrow. Okay. Well, so there's another way that you can imagine reducing the collision velocity, and that's been done at Amy Cotton by Nicholas Sampé and his his collaborator, namely Nicholas von Eyck and Pierre Piet. So they used a supersonic beam. And so while the beam itself is moving extremely rapidly, I mean, the velocity spread is very small, something like a 1 Kelvin beam. Okay, so this is the same kind of level crossing that I showed you earlier, which is partly why I showed you. So, and their initial state is sodium again, it's 248S atoms. And they come into resonance with this 48P and 47P, this field of about 4 volts per centimeter. So what they in fact did was to apply a pulsed field to this that brings atoms excited in zero field out, I mean, either up to this point or not quite to it, and then they in fact look at the probability of transitions from this pair of 48S states up to this pair up here, which they detect by seeing the higher line 48P state. So the way they do this, of course, is to use a pulse that looks like this. And so the atoms are so cold that during the rising and falling edges of this pulse, they essentially don't move anywhere, but they can, of course, move during the center of the pulse. Okay. So if you look at this picture, it's clear that if you go through this crossing, both diabatically twice or adiabatically twice, nothing happens. And so, or at least you don't make any transfer up to the other state. So you have to have one adiabatic and one diabatic transition. And so the two ways that you can get a signal are, if the atoms are initially close together, on the rising edge of this pulse, they follow this adiabatic curve. And then while the pulse, the voltage pulse is sitting up here, the atoms move apart. And then when you go back, they of course then follow diabatically down here, but they're still left in this state. Conversely, if they are initially far apart, they go through like this, and then if they move together, then on the falling edge, they can in fact follow the adiabatic path. But in either case, you wind up making the transition from the SS to the P2' state. So this is what they see for 3 different states. When the pulse gets to the avoided crossing, you see this big peak, which I presume comes from the atoms just sitting. This is the resonance. So here you can actually have a collision like the ones I was describing earlier. But once you're out in this plateau region, basically the only way you can get that signal is in fact to have one adiabatic passage and one diabatic passage through that avoided crossing. Okay, so, but in either case, you're assuming that the atoms aren't moving while the field pulse is either rising or falling. So this is essentially the assumption that's made in treating atoms in mods. So in a magneto-optical trap, where the typical temperatures are 300 microkelvin, if you have a density of 10 to the 9th per cubic centimeter, so the typical spacing between the atoms is 10 to the minus 3 centimeters. For reference, if you make an n equal 30 atom, its diameter is 10 to the minus 5 centimeters, which you can't see on this scale. So it's still true that the atoms are not overlapping with each other. They're separated by 100 times the radii. The other interesting thing is that if you do an experiment in a time scale of 1 microsecond, the speed of the atoms is 20 centimeters per second, so they go about this far, 2 times 10 to the minus 5 centimeters. In other words, they move an amount that's comparable to their diameter. So in principle, they're not moving, and on 1 microsecond time scale, the atoms are frozen just like this, except they're about a factor of 10 smaller than shown here. So there is no such thing as a collision in this system, which is often called the frozen Rydberg gas. In fact, it's much more like an amorphous solid. Okay. Nonetheless, you can still see resonant energy transfer. So in a random gas, such as this one, much of the effect is due to the nearest neighbor atom. So it's, in that sense, and I'll come back to it, it's similar to the binary collision problems that we've been discussing up to now. So, for example, this pair interacts primarily with each other. On the other hand, it's clear that this atom is not much further away, much closer than this one, and so it's not obvious that you can ignore this one. So you in fact expect that many body effects are going to be important, since the next nearest neighbors aren't much further away than the nearest neighbors. Okay. So this is an important difference from a collision process, is that in a collision, basically they move past each other. They don't have to be statically close to each other. You just have to pass near each other. Okay. So so this is quite an important difference. Okay. So one of the first experiments done on this topic was in cesium. And so it's essentially the same principle as the sodium experiments and potassium experiments I described earlier. Two cesium atoms placed in this 24p 3-half state are halfway between the 23s state and the 24s state. And the fields at 80 volts per centimeter, they're exactly resonant. And a similar experiment was done coincidentally with rubidium, in which atoms are placed in two different states, and one can go up to 34p, and one can go down to 24. But in the cesium experiment, if they populated that 24p state and look for population in the, 23p and look for population in 24p, they see resonances that in fact broaden as you raise the pressure. So in the collision experiments, you don't get broadening as you raise the density. You can, unless you actually saturate the number of atoms that's undergoing the collision, which is not happening here. However, they are broadening. The other so this is clearly not a collision. The other interesting thing is that these resonances are about 10 times as wide as they originally expected. We also had the same expectation based on the average spacing. Okay? In other words, if you plugged in the average spacing, the dipole-dipole interaction that was driving this transition, you would get widths that are roughly 10% of what you see.